Welcome back to another video. Today, we will explore simple linear regression by learning how the intercept and slope are estimated using the least squares method and by demonstrating how to compute and interpret these results in Python. In simple linear regression, we study the relationship between one independent variable, also called a predictor, and one dependent variable, also called a response. We usually denote the predictor by x and the response by y. In this model, beta 0 is called the intercept and beta 1 is called the slope. These are unknown regression coefficients that describe the linear relationship between the predictor and the response. We assume that each observed response value, called y, can be described by this model. Y equals beta 0 plus beta 1 times xi plus epsilon for each observation, and epsilon represents the random error term associated with each observation. We further assume that the error term follows a normal distribution with a mean of 0 and a variance of sigma squared. This assumption captures the idea that not all variation in the response can be explained by the predictor alone, and that the unexplained variation is random and centered around 0. To find the most probable, or expected, value of the response variable y for a given value of x, we compute the expected value of y given x. Taking the expected value of the regression model gives the expected value of beta 0 plus beta 1 times x plus epsilon. Because beta 0 and beta 1 are constants, their expected values remain the same. In addition, since the error term has an expected value of 0, the expected value of epsilon is 0. As a result, the expected value of y given x simplifies to beta 0 plus beta 1 times x. In practice, we do not know the true values of beta 0 and beta 1, so we replace them with their estimates, called beta 0 hat and beta 1 hat. Therefore, the estimated expected value of y given x is beta 0 hat plus beta 1 hat times x, which represents the predicted value of the response for a given predictor value. Now, the question is how we can find the best values for the intercept, beta 0, and the slope, beta 1. These two values determine the shape and position of the line that models and explains the relationship between our independent variable, x, and our dependent variable, y. Different choices of beta 0 and beta 1 will produce different lines, each representing a possible explanation of how the response variable changes with the predictor. Our goal is to select the values of beta 0 and beta 1 that result in a line that best fits the observed data, meaning it comes as close as possible to the observed values across all data points. For all 20 observations, we already know the hydrocarbon levels and their resulting oxygen purity. Let's assume that we have a fitted line such as beta 0 hat plus beta 1 hat times x. Using this fitted line, we can find the expected oxygen purity for all 20 observations based on the existing levels of hydrocarbon. So, for each observed hydrocarbon level, we have an observed oxygen purity reported by the chemist, the red dots, and an estimated oxygen purity reported by our fitted line, the purple line. For each observation I, we can measure the error, epsilon I, as the difference between the observed and estimated oxygen purity. To measure the total error produced by a fitted line, we might consider simply summing the errors across all 20 observations. However, doing so would risk underestimating the overall error. This is because some errors are positive, corresponding to observations that lie above the fitted line, while others are negative, corresponding to observations that lie below the line. When summed directly, these positive and negative errors can cancel each other out, giving a false impression of a better fit than actually exists. To avoid this issue, we square each error before summing them. Squaring ensures that all errors contribute positively to the total and gives greater weight to larger deviations. The resulting quantity is called the sum of squared errors. The least squares method then chooses the line that minimizes the sum, which is why the resulting estimates are known as least squares estimators. To find the best fitted line, we use the least squares method, which chooses the values of beta 0 and beta 1 that minimize the total squared difference between the observed response values and the values predicted by the regression line. The least squares method squares each residual and then sums these squared residuals across all observations. To find the optimal fit, we treat the sum of squared residuals as a function of the two unknown coefficients, beta 0 and beta 1, and take partial derivatives with respect to each coefficient. Setting these derivatives equal to 0 produces two equations, known as the normal equations. The first normal equation ensures that the residuals balance out so that their total sum is 0, while the second ensures that the residuals are also balanced when weighted by the predictor values. Solving these two equations simultaneously leads to closed-form expressions for the least squares estimates. The slope estimate is given by the ratio of how x and y vary together to how x varies by itself, capturing the strength and direction of the linear relationship. Once the slope is determined, the intercept is obtained by forcing the regression line to pass through the point defined by the sample means of x and y. Together, these estimates define the unique line that minimizes the overall squared prediction error and therefore best fits the observed data in the least squares sense. We also have an exercise here that is asking to check the second derivatives. This exercise is important because it confirms that the least squares solution corresponds to a true minimum of the error function, ensuring that the estimated regression line is optimal rather than a maximum or a saddle point. Returning to our example, we consider a chemist who is producing oxygen through a complex chemical process. Based on 20 experimental runs that have already been conducted, the chemist knows that the purity of the oxygen produced depends on the level of hydrocarbon present in the raw material. Our goal is to determine whether these prior observations can be used to construct a simple linear regression model that estimates the oxygen purity before running a new experiment. Using the provided dataset, we denote the hydrocarbon level as x and the oxygen purity as y. From the data, we compute the sum of squared deviations of x from its mean, the sum of the products of deviations of x and y from their means, as well as the sum of x values and the sum of y values. Substituting these quantities into the derived closed-form expressions for the least squares estimates, we obtain a slope estimate, beta 1 hat, of 14.95 and an intercept estimate, beta 0 hat, of 74.28. As a result, the fitted regression model indicates that the expected oxygen purity equals 74.28 plus 14.95 times the hydrocarbon level of the raw material. This model allows the chemist to predict oxygen purity in advance and better understand how changes in hydrocarbon levels influence the outcome of the process. Rather than performing these calculations by hand, we can use Python to carry them out efficiently. We begin by importing the dataset and then use the stats models library to fit a least squares regression model. To ensure that the model includes an intercept, we must use the add_constant function to add a column of ones to the predictor matrix. Once the dataset is properly structured, we can call the OLS function from the stats models library to fit the model. Finally, we use the summary function to display a detailed overview of the fitted model, as shown on the right side. The regression summary combines information about what relationship was estimated, how well it fits, and how uncertain that estimate is, all in one place. As we dive deeper in simple linear regression, we will explore the meaning behind these different sections and numbers. For now, we will focus on the middle section of the results table. In this part, the coef column contains the numerical estimates of beta 0 hat, the intercept, and beta 1 hat, the slope, which together define the fitted regression line. Thank you for watching. I hope this video was helpful, and I look forward to seeing you in the next one.